Welcome to this next video in the playlist on field theory. In this video, what we're going to discuss is the composite of two fields. Okay, so the first thing to say is that this is going to be a rather dull video. Okay, we're discussing the composite of two fields, not because it's an interesting topic in itself in particular, but because it's something that we're going to need in proofs that are going to appear later in this series on field theory and beyond. Okay, so really this video is an introduction to a piece of machinery that we're going to use to prove something that's interesting, but in itself is a little bit dull. Okay, so that's the first thing to say, that this is necessary, but it's not going to be particularly interesting. Okay, so what we're going to do then is we're going to start off with the definition of the composite of two fields, okay, and then we'll have a look at two interesting facts that will help us better understand the composite of two fields. Okay, so let's start off then with the definition. So, what we need then in order to define the composite of two fields is of course two fields. Okay, and we're going to imagine that these are in some larger field. So we're going to have K1 and K2, which are going to be our two fields, and we're going to imagine that they're in some larger field, capital L. Okay, and then what we're going to do is define what the composite of these two fields is. So let me draw a picture of this then. So this large box here, this will represent our largest field, capital L, and we'll colour in capital L here in green. Okay, so now next what we need to do is mark on this picture the two fields K1 and K2, which are going to be subfields of L. Okay, so we'll start off with K1, so we'll let K1 equal this box here, so this is going to be K1, so I'll outline K1 here in the orange, like so, and we'll also have K2 in here. And of course K2 and K1 will have a non-empty intersection because both of them have to contain the additive identity and the multiplicative identity from L, so I'll have them intersecting here with a non-empty intersection. Okay, so this is going to be K2 here, and we'll colour K2 then in vivid purple here, like so. Okay, so we're ready now to define what the composite of these two fields is, what the composite of K1 with K2 is. Okay, so firstly, how do we denote the composite of the two fields? Well, you just write K1 and then next to it you put K2. So when you see K1 next to K2 like this, you should read this as the composite of the field K1 with K2, or just the composite of K1 with K2, or the composite of K1 and K2. Okay, so how is this defined then? This is defined, so the sort of informal line that you can state if someone asks you for the definition of the composite of two fields is that it's the smallest subfield of our larger field capital L, which contains both K1 and K2. Okay, so it itself is going to be a subfield of L, and I know this is just the symbol for subset, but there isn't a sort of unanimously agreed symbol for subfield, so I'll write it and say subfield, but I know it's the symbol for subset. Okay, so K1, K2, the composite of K1 and K2 is going to be a subfield of capital L, and it's going to be the smallest subfield of L, which contains both K1 and K2, so I'll write that down. K1 is going to be completely contained within the composite of K1 and K2, and also K2 is going to be completely contained within the composite of K1 and K2. Okay, so now let's do more rigorous. So the smallest subfield of L that contains both K1 and K2, what is the rigorous interpretation of that? Well, of course, we've seen this before, a very similar thing before, where we've talked about the field generated by a bunch of elements, the extension field of a certain field generated by a bunch of elements being the smallest subfield that contains the initial field and all of those generators. Okay, so the way we're going to do this is we're going to say, look at every possible field extension of K1 and K2, and note that the composite of K1 and K2 is going to be a field extension of both K1 and K2. So look at all fields, and I'll call them E. Okay, so we'll look at all the subfields of L, E, which are field extensions of both K1 and K2. Okay, so E has to contain K1 and K2. It has to be a field extension of K1 and K2. Okay, and it itself is going to be a subfield of L. Look at all of these subfields of L which contain both K1 and K2, and then intersect every last one of them together. So now consider the intersection of all such fields E, and I might put EI here, where you intersect over the I, which is an element of some index set. So you just look at every possible subfield of L which completely contains K1 and K2, and you intersect all of them together. Okay, now, of course, every single one of these EIs is going to be a field extension of both K1 and K2. So when you intersect them all together, you're going to end up with something that still contains K1 and K2. You're going to end up with a field extension of K1 and K2. And we know from our video on intersection of fields earlier on in this playlist on field theory that when you intersect loads of fields together in this way, the thing that you end up with is still going to be a field, provided that it isn't empty. Okay, so we know that this is still going to be a field extension of K1 and K2. It's still at the very least going to contain K1 and K2. Okay, so we do indeed know that when we intersect all of these subfields of L which contain K1 and K2 together, we'll end up with another subfield of L. Okay, and this one now is still going to be a field extension of K1 and K2, and indeed this is what we're going to be calling the composite of K1 and K2, so this is going to be equal to the composite of K1 and K2, and it is indeed going to be a field extension that completely contains K1 and K2. Now, why is it going to be the smallest one? Well, because if you take any other field extension of K1 and K2, any other subfield of L which completely contains K1 and K2, then this thing is going to have to be contained within that, because that field extension of K1 and K2 will be one of the things that you intersect together to make this. Okay, so this overall answer here must be contained within every single one of these things that you've intersected to make it. Okay, so truly it is the smallest subfield of L that contains K1 and K2. So there is the definition of the composite of two fields. So for the rest of this video then, what we're going to do is try and understand a few important little facts about composites of two fields. Okay, we're going to develop our understanding of this, and as I say, this is not an end in itself. This is a means to an end. This is a piece of machinery that we're going to make use of in future videos, which is why I'm introducing it here rather than having to go over it and introduce it when we're doing those proofs in the future. It's worthwhile doing it before we actually get to the proofs so that we're familiar with it. Okay, right, so first interesting claim then about composites of two fields. So claim number one, and I've got two interesting claims to improve your understanding of these things. Okay, so here comes the first one. Okay, so we're now going to assume that K1 and K2 are themselves field extensions of some initial field capital F. Okay, so I'm going to assume that both K1 and K2 are field extensions of F. So if you like, on this picture, you can imagine that this portion here, or a sub-portion of that intersection between them, we'll just go for the entire intersection, is a field capital F. Okay, so I'll just highlight this in. So all of this bit in purple, we're now going to imagine that that's a field capital F. As I say, it doesn't necessarily need to be the entire intersection of the two. It could just be a sub-portion of the intersection. But to make the picture look simpler, I'll just go for the entire intersection there. Okay, so we're now going to imagine that both K1 and K2 are themselves field extensions of F. Okay, we're also going to imagine that they are finite field extensions of F, i.e. that the degree of K1 over F is equal to some finite natural number, which I'll call little m here, and that the degree of K2 over F is also equal to some finite natural number, which I will call m. Now note, if these are finite field extensions of F, then we know from our study of algebraic field extensions that we can instantly conclude that K1 and K2 are algebraic field extensions of F. Okay, so we know from the video on algebraic field extensions that if your field extension is finite, you can conclude that it is algebraic, i.e. that all the elements in that field extension are algebraic over F, and we will use that fact later on, so just bear that in mind for now, but we'll come back to it later on. Okay, so we're going to assume that both of these field extensions are finite field extensions of F, okay, and I haven't actually put the claim yet. This is all just the startup for the claim, okay, this is all just the setup, and then I'll put the claim in a moment. Okay, so we're going to assume this. Now, what does this mean? This means that K1 can if we view it as a vector space over F, we can construct a beautiful finite basis with n basis vectors in it, and I'll call this B1. Okay, so it's going to have vectors V1, V2, all the way up to Vn, and this is necessary. We are going to have a theorem that concerns this, which is why I'm putting all this in the setup. Okay, so all these Vi's are going to be elements of K1, so that's my basis for K1 viewed as a vector space over F. So of course, if it's a finite field extension of F, then it is possible to do this, and I'm just calling the basis vectors arbitrarily V1, V2, all the way up to Vn. And similarly for K2, if K2 is a finite field extension of F, then I can write a basis for it as well, and we're saying that its degree is m, so we'll call this B2 this time, and we'll have the vectors W1, W2, all the way up to Wm, where all of these, of course, the Wi's, are elements of K2 there. Okay, so that's all perfectly fine. Okay, this is all stuff that we know. If these are indeed finite field extensions of F, then you can come up with these bases for them, viewed as vector spaces over F. So that's all absolutely fine. So now here comes the claim. Here comes the new bit. The claim now, which is coming back to this definition of the composite. The claim now is that if you form the composite of K1 and K2, and by the way, we're still imagining that K1 and K2 themselves are contained within some large field, capital L. So we are imagining this picture. We've got some little field F, we've got these intermediate fields K1 here and K2 here, and then we've got the gigantic field L. And we're now thinking about these being finite field extensions over F, and we're now considering the composite of K1 with K2, and we're about to have a beautiful claim as to what this is going to be equal to. Okay, so here comes the claim that this thing, the composite of K1 with K2, is equal to the field extension of F generated by all of these basis vectors here. So the field extension of F generated by V1, V2, all the way up to Vn, and then we don't stop there, I want these ones in as well, W1, W2, all the way up to Wn. Like so. So remember, this is going to be the smallest field extension of F that completely contains all of these elements. Okay, so you can hopefully appreciate that that might be a useful theorem to understand about composites. Okay, so my claim then is that if we can view K1 and K2 as field extensions of some field capital F, and they're finite field extensions of this initial field capital F, then we can form these basis vectors, and then the composite of K1 with K2 will just be equal to the field generated by all of the basis vectors over the field capital F. Okay, so now for the proof of this. Proof. So how are we going to prove this? Well, it's going to be our standard strategy for proving that two sets are equal to one another. We're going to prove containment both ways around, and therefore we'll be able to conclude that the two are absolutely equal to one another. Okay, so one way is easier than the other way, so we'll start off with the easy way. The easy way to conclude is that the field extension of F generated by V1, V2, all the way up to Vn, and W1, W2, all the way up to Wm, that this is completely contained within the composite of K1 and K2. That's the easy one to conclude. Now, why is that easy to conclude? Well, this is the smallest field extension of F that contains all of these elements. The composite of K1 and K2 is going to have to be a field extension of F, because F is contained in both K1 and K2, and this contains both K1 and K2 by definition. Okay, so F is going to have to be contained in this, so this is a field extension of F. It's also going to have to contain all of these basis vectors here, so V1, V2, all the way up to Vn, W1, W2, all the way up to Wm, because all of these, as I've written here, are contained in the K's. So all the Vi's are contained in K1, and all the Wi's are contained in K2, and this has to contain K1 and K2. Okay, so indeed, this is going to contain F, so I might just write this down. So F is going to be contained within the composite of K1 and K2. All of the Vi's are going to be contained within K1 and K2, they're all going to be elements of K2, and all of the Wi's are going to be elements of K1, the composite of K1 and K2. Okay, so that then means that this is a subfield of L which completely contains F and it contains all of these elements. How do I create this thing? I look at all subfields of L that contain F and all of these elements, and I intersect them all together. So this would have been one of the things that I intersected together when I produced this thing, and therefore I can easily conclude that this must be contained within the composite of K1 and K2. Excellent. Now to prove the other way round. Okay, so how am I going to conclude the other way around? Well, to start with, I need to prove that K1 and K2 are completely contained within this. And then, of course, this will be a subfield of L which contains K1 and K2, and therefore it will be one of the things that we intersect together to make the composite of K1 and K2. So hopefully you'll agree that if I can prove that K1 and K2 are both contained within the field extension of F generated by all of these basis vectors, v1, v2, all the way up to vn, w1, w2, all the way up to wn. Okay, so if I can prove that, then hopefully you agree that I can prove that K1, the composite of K1 and K2 is going to be contained within this, because after all this will be a subfield of L which completely contains both of these, and therefore it'll be one of the things that we intersect together to make K1 intersect K2, and therefore the composite of K1, K2, not the intersection of K1 with K2. So therefore the composite of K1 and K2 will be completely contained within this thing. Okay, so all I need to prove then is that K1 and K2 are completely contained within the field extension of F generated by v1, v2 all the way up to vn, and w1, w2 all the way up to wn. Okay, so how am I going to do this? Well, this comes back to the fact that these are both algebraic field extensions over F. So remember, because they're both finite field extensions over F, we can conclude that they're both algebraic field extensions over F, which means that all of the elements in them are algebraic over F. In particular, all of these basis vectors which are in them are algebraic over F. So this is a finitely generated field extension of F where all of the elements that you're using as the generators are algebraic over F, and we know how to construct such a thing. Okay, what you have to do is you have to look at the ring of polynomials in how many indeterminates are we going to need. We're going to need n for these lot and m for these lots, so we're going to need x to the m plus m will be our highest indeterminate. So we'll have the ring of polynomials in a lot of indeterminates, x1, x2, x3 all the way up to x to the n plus m here. Okay, and then if you want to construct this thing, all you have to consider is evaluating all of these polynomials where you let x1 be evaluated at v1, x2 be evaluated at v2, x3 be evaluated at v3, etc. And then you'll go all the way up and x to the n plus m will be evaluated at wn. So you've got one of these indeterminates for each of these basis vectors that we have here. Okay, and if you work out what all of these polynomials evaluated at these elements are, they will all be elements of the gigantic field L. You collect all of the answers together, and that is going to be the field extension of F generated by all of these elements. That's something we discussed in the video on finitely generated field extensions, how to actually construct this thing if all of the generators are algebraic over F. Okay, and because they're algebraic over F, you will not continually get new answers. Okay, so when you go through all the polynomials in here, eventually, you know, it will loop back around. Okay, you won't just go through more and more higher and higher degree polynomials and keep getting new answers in the field capital L. Eventually it will start looping back around and you won't be getting new answers, you'll be getting the same answers that you've already got, hence why this thing will end up being a finite field extension of F. Okay, but this is how you construct it fundamentally. You look at all the polynomials in here and you evaluate them at these basis vectors here, which are your generators. Okay, and as I say, that only works if we know that these are algebraic over F. If you don't know they're algebraic over F, then it could be the case that, well, if they're not algebraic over F, it will be the case that the polynomials will never start looping back round. Okay, you'll just go on and on through all of those polynomials, higher and higher degrees, and you'll just continuously get new answers. Okay, and it won't end up ever looping back around. Okay, so it does rely on these being algebraic over F, which we know they are going to be. Okay, now, how then does this help me understand that K1 and K2 will be completely contained within here? Well, I know that anything in K1 can be written as an F linear combination of these basis vectors, v1, v2, all the way up to vn, and I know that anything in K2 can be written as an F linear combination of these basis vectors, w1, w2, all the way up to wn, whereby F linear combination, all I mean is a linear combination of those basis vectors where the coefficients are from F. Okay, so, but look at we are looking at all polynomials with coefficients in the field capital F, okay, and evaluating them at this. So we'll certainly get polynomials which will give us every possible linear combination. So for instance, look at the polynomials of the form a1 x1 plus a2 x2 plus all the way up to an x to the n. That will certainly be a polynomial in this great ring of polynomials in all of these indeterminates. Yes, it doesn't have all of the indeterminates appearing here, but then it doesn't need to. Okay, it doesn't need to have all of the coefficients in front of all of the indeterminates non-zero. Okay, it just has the coefficients a1, a2, all the way up to an, which are in front of x1, x2, all the way up to xn non-zero. All the others are going to be 0. Now, why am I so interested in this polynomial? Well, of course, when you evaluate this, when you evaluate a polynomial of this form, according to this mapping here, then you'll let x1 equal v1, x2 equal v2, etc. So what you'll end up with is something like this, a1 v1 plus a2 v2 plus all the way up to an vn, and you'll be looking at what this value is in the field capital L, and of course you can get anything that's in the field capital K1 by doing this, because we know that everything in capital K1 can be written as a F linear combination of these basis vectors, and you can let a1, a2 all the way up to an here equal whatever you like in the field capital F. Okay, so truly, you can find a polynomial in here which will allow you to find every single element of K1. So when you construct this thing, you will get all the elements of K1, and the same argument holds for K2. In that case, what you'd want to look at is the polynomials that say b1 x to the n plus 1 plus b2 x to the n plus 2 plus all the way up to bn x to the n plus n. You just look at these polynomials where again the b1, the b2, all the way up to the bn, they can vary over any element of the field, and of course when you evaluate those, x to the n plus 1 will be carried on to w1, so this will go to w1, x to the n plus 2 will go on to w2, x to the n plus m will go on to wn, so you'll get any linear combination of these basis vectors, and of course that will give you every element of K2, where you can vary these as you need to get every element of K2. Okay, so truly, when you construct this thing, you will end up getting every element of K1 and K2 because of our understanding of how you construct this thing by looking at all of these polynomials in these m plus m indeterminates over the field F and evaluating them at these basis vectors. Okay, so truly you will end up with all of these elements, and we know that these are going to give separate elements because of the fact that these are basis vectors for these field extensions of F. Okay, which means that they will be linearly independent, and therefore all of the linear combinations must be different answers. Okay, right, so that is then why we can conclude that K1 and K2 are going to be subsets of this field extension of F generated by all of these basis vectors. And now that we know that those two things are contained within this, then this is a subfield of L which completely contains K1 and K2, so it's one of the things that you will intersect together to make K1, K2, the composite of K1 and K2, and therefore you can conclude that K1, K2, the composite of K1 and K2 must be contained within this field extension of F generated by all of these basis vectors, and hence you've proven containment both ways around, and you can now conclude that these two are indeed equal to one another. Okay, right, so I think we'll have a break there, and in the next video we'll look at my second important claim to improve our understanding of the composite of two fields.